My dear students, let me welcome you all to a new edition of physics. In this edition, we'll resume revising chapter 1. We'll revise applying Ohm's law on closed circuit, the relation between EMF of a cell and its terminal voltage. And you'll be encountered with miscellaneous questions. So let's get started. Ohm's law applied to a closed circuit. First of all, what is the definition of electromotive force of a cell? EMF or V battery? Electromotive force of a cell. It is the work required to transfer unity charge. Unity charge means one coulomb through the whole circuit. Through the whole circuit means through the external circuit, overcoming external resistances, and the internal circuit. So it is the work required to transfer unit charge through the whole circuit. That's to say, through the external circuit as well as the internal circuit. Also, EMF of a cell is defined as the terminal voltage of the cell when no current passes through it. Once again, EMF of a cell is the terminal voltage when no current flows. In front of you, we've got a circuit, a very simple one, a cell connected to a load denoted by R. And of course, they are connected in series. Same current passing through the cell and the load, the resistance. It is denoted by I. Okay. EMF of a cell work to transfer one coulomb through the whole circuit. Okay, through the external and the internal. So it is equal to V external plus V internal. V battery equals V external plus V internal. So it is equal to IR capital plus IR small. V battery equals IR capital plus IR small. I is taken as a common factor between two brackets R capital plus R small. And in this way we can obtain the current passing through the battery, the main current. Okay, of course, R is the external resistance, R small is the internal resistance of the battery. And current passing through the battery is given by the expression V battery over R capital plus R small. This is Ohm's law applied to a closed circuit. So it follows I is the current through the battery. So I equals V battery over R equivalent of the whole circuit, R capital plus R small. The previous relation, as I said, is called Ohm's law of a closed circuit. Your attention, please. V external is also called terminal voltage. Okay, V external is called terminal voltage. And what about V internal? V internal is called lost voltage. V external plus V internal gives V battery. V external is called terminal voltage, and internal voltage is called also lost voltage. Okay, and now we've got questions. What would happen to the readings on the voltmeters? The two voltmeters, if the value of R1 was increased. Okay, so R1 is a variable resistance. We'll increase the value of R1. And what effect does this have on V1 and V2, the two voltmeters? Okay, let's calculate it together. Let's do it together. Okay, increase in R1 will increase the total resistance of the whole circuit. So the current passing through the battery will be decreased. So internal voltage, which depends on the current, internal voltage equals IR small. R small is constant, so it depends on the current. Okay, decreases. When internal voltage decreases, external voltage increases. So V1 increases. And what about V2? V2 depends on the current because it is calculated by the product of the current and R2. R2 is constant. So what happened to the current? Yes, it was decreased. So V2 decreases. Okay, once again, V1 increases, but V2 decreases. V1 increases, but V2 decreases. When R1 is increased, R total increases, current decreases, internal voltage decreases, external voltage, which is denoted by V1, increases. And V2 depends on the current, so it decreases. Once again, since the current passing through the circuit, current through the battery, is given from the expression V battery over R equivalent of the whole circuit. So the current is inversely proportional to the total resistance because V battery is constant for a given cell. V internal is equal to IR small. So internal voltage depends on the current. R small is constant for a given cell. Okay, V battery equals V external plus V internal. So external voltage and internal voltage equals constant. So when external increases, internal decreases. Okay. So when V internal decreases, the external voltage increases. And when R1 increases, so we'll take it one by one, the current through the circuit decreases because R total increased, and so does the internal voltage. Internal voltage decreases, and when internal voltage decreases, external voltage increases. So V1 increases. And what about V2? It is given by IR2. R2 is a constant, so it is proportional to the current, and current was decreased, so V2 decreases. Another question, what would happen to the reading on the voltmeter when R1 was increased? Your attention please, we need to know, yes, what exactly this voltmeter reads. It reads the voltage across R2. Okay, voltage across R2 is given by the relation IR2. R2 is constant, so it depends on the current. If the current increases, it will increase. If it is decreased, it will, yes, decrease. R1 was increased. Increasing R1 will decrease the current. Okay, so the current passing through R2 will be decreased. Voltage across R2 will be decreased. This voltage is read by V1, so V1 decreases. The voltmeter reads voltage on R2, as I said. The reading on the voltmeter equals IR2. Value of R1 increased, the current decreases. So the reading on the voltmeter decreases because R2 is unchanged. Another interesting question, what would happen to the readings on the, yes, voltmeter and ammeter when the switch is closed, switch K2 is closed? Okay, so what would happen when closing K2? As a matter of fact, this will disconnect R1. Disconnecting a resistance means we are decreasing the resistance. So the current increases. Reading of the ammeter will be increased. Voltmeter located, mounted on the cell, reads terminal voltage. Okay, when the current increases, internal voltage increases, external voltage or terminal voltage decreases. So V decreases, but the current increases. Once again, V decreases, but the reading of the ammeter increases. Another type of questions: when does the value of the terminal voltage of a cell equal the EMF of the cell? Let me say it again. When does the value of the terminal voltage of a cell equal the EMF of the cell? Of course, when no current passes through the cell. Okay. The terminal voltage of a cell equals the EMF when no current passes through the cell. Another, when does the value of the terminal voltage of a cell equal 0? Okay, it's all easy. When the cell is short-circuited. Okay, what does it mean short-circuited? When it is connected to 0 ohmic resistance. Okay, so the answer is the value of the terminal voltage of a cell equals 0 when the cell is short-circuited. When does the value, another question, when does the value of the terminal voltage of a cell becomes greater than EMF of a cell? Okay, as a matter of fact, this happens when the cell is being charged. Value of the terminal voltage of a cell, okay, becomes greater than EMF of a cell while the cell is being charged. Choose if the EMF of a cell of internal resistance R is 1.5 volt. EMF equals 1.5. The cell has internal resistance, okay, denoted by small r. The terminal voltage of the cell when a current passes, when a current flows through the cell is 1.5, more than, greater than 1.5, less than 1.5, no correct answer. Of course, it is, yes, less than 1.5. Okay, thank you very much. Another choice, two bulbs having resistances R1 and R2 connected in series to a DC supply. Connected in series means they, yes, carry the same current intensity. Same current intensity passes through both of them. R1 is greater than R2. R1 is greater than R2. Okay, the ratio of the brightness of the first to that of the second is greater than, equal to, less than 1. When connecting in series, brightness is the power, okay? It is directly proportional to the resistance. So which one of them has the higher resistance? The first. So it will glow, yes, more. So it will be greater than. Okay, thank you. Now we've got another type of questions. We've got the circuit here. Okay. We've got 3 meters here, 2 voltmeters and an ammeter. One located, mounted on the cell, V1, and it measures external voltage. V2 measures the voltage across the 3 ohm, and the meter measures the current passing through the circuit. Okay, V1 and V2. V1 is the reading read by the first voltmeter. V2 is the reading read by the voltmeter, yes, mounted across the 3 ohm resistor. We've observed something here. When the key is open, okay, when the key is open, this means no current passes through the cell. In this particular case, V1 will be equal to the EMF of the cell. V1 is 9 volt, so EMF, okay, is 9 volt. And V2, what about V2? It must be 0, okay, because no current passes through the 3 ohm resistor. When it is closed, the voltage V1 will drop. It will be 7.5. So external voltage now is 7.5. Okay, and voltage across the 3 ohm is 4.5. Use the previous diagrams to calculate the value we want you to calculate, value of R capital and internal resistance of the cell. Then find the reading on the ammeter when the circuit is switched on. Okay, V battery, as I said, is equal to 9 volt. Okay, but V external 7.5. It's all easy to calculate the internal voltage. It is the difference. 9 minus 7.5, it is 1.5 volt. Okay. Voltage across the 3 ohm is 4.5. Voltage across the 2 resistors 7.5. Okay, so we can calculate the voltage across the second resistor. First of all, current passing through the 3 ohm resistance, it is 4.5 over 3. Voltage over, yes, resistance. So the current is 1.5. V internal 1.5, current 1.5, internal resistance is 1 ohm. Okay, potential difference across R, across the unknown resistance, is 7.5 minus 4.5. It is 3 volt. Okay, this is potential, so it is equal to, yes, we can calculate from it the resistance. Resistance equal potential over current. 3 over 1.5, it is 2 ohm. Another circuit, okay, in front of you you've got, yes, a cell connected in series to an ammeter, resistor and a switch. And we've got a voltmeter, yes, connected across the cell. The figure shows a circuit in which the voltmeter reads 12 volt when the switch is open. This reading is equal to V battery. The question is why? Because the switch is open, no current flows. So terminal voltage is equal to EMF in this case. Okay, so V battery is given to be equal to 12 volt. But when the switch is closed, the voltage drops to 9 volt. 12 V battery, V external 9, so it will be so easy for you to calculate internal voltage. And the meter reads 1.5 ampere. Okay, find the value of R capital and R small. And if R capital is replaced by a resistance of 8 ohm, what is the new reading on the voltmeter? Okay, we'll take it one by one. V battery, as I said, is equal to 12. V external equals 9. So V internal must be equal to 12 minus 9, it is 3 volt. Current, okay, is given 1.5. So R internal equals 3 over 1.5, it is 2 ohm. The resistance equals voltage, which is terminal voltage 9 over 1.5, it is 6 ohm. And when R is replaced by a resistance 8 ohm, okay, we need to calculate the new current. First of all, let's calculate the total resistance. The new total resistance equals 8 plus 2, it is 10. Current equals 12 over 10. 12 is the V battery, so it is 1.2 ampere. And V external equals IR external, so 1.2 times 8, it is 9.6 volt. This is the reading on the voltmeter because it reads, yes, external voltage. Okay. Another question, what is the mathematical relation between the voltage read by each voltmeter? Okay, V1 reads terminal voltage. V2 reads the voltage across R2. We want you to give the relation that relates both of them. Okay, and the current intensity flowing through the circuit. And show that when the value of R1 is changed such that the reading on the voltmeter V1 is increased and reading on the voltmeter V2 is decreased. Okay. The relation is V1, which is terminal voltage, equals V battery minus internal voltage. Internal voltage is IR small. Okay, now we managed, yes, to relate the readings of the two voltmeters, okay, and the current. V2, the reading of the second voltmeter equals IR2. Okay, V1, terminal voltage, is equal to V battery minus IR. When R1 is increased, okay, the equivalent resistance of the whole circuit is increased. Explanation, okay, since I is given from V battery over R equivalent of the whole circuit, okay, if we decrease the equivalent resistance, if we decrease the equivalent resistance, the current increases. If we increase the equivalent resistance of the whole circuit, the current decreases. We've got an inverse relation, okay? So I is inversely proportional to the equivalent resistance of the circuit because V battery is constant. V internal, since it is equal to IR small, so it depends on the current. It is proportional to the current because R small is constant. Since V battery is equal to V external plus V internal, V battery is constant for a given cell, so we expect an inverse relation between V external and V internal. When V internal increases, V external decreases. Okay, because the sum of both of them equals constant. When V internal decreases, external voltage increases, as I said. Okay, now we can take it one by one. R1 increases. When R1 increases, current through the circuit decreases. And so does the internal voltage. Okay, when internal voltage decreases, the external voltage increases. So V1 increases. V2 equals IR2, so it depends on the current. V2 proportional to the current, okay, since R2 is constant. So when the current decreases, V2 decreases. We've got another question. 3 identical lamps are connected across a battery of negligible internal resistance. 3 identical lamps. Okay, once in series and then in parallel, each at a time. Prove that the ratio of the powers dissipated in the two cases is 1/9. prove that the ratio of the powers dissipated in the two cases is 1/9. In series connection, we'll calculate the power. First of all, we need to calculate the total resistance. R equivalent equals 3R. Current I1 equals V battery over R equivalent over 3R. So I1 equals VB over 3R. Power is given from the expression IR squared, okay, for the whole battery. For the whole circuit, it is I1 squared, R equivalent, okay. So it is equal to VB over 3R squared times R equivalent, which is 3R. So the power is given by VB squared over 9R squared times 3R. This can be, yes, abbreviated into, okay, R will be crossed out, and we can say P1 equals VB squared over 3R. This was about when connecting the three resistors, the three pulps in series. The power is calculated from the relation VB squared over 3R. In parallel, R equivalent equals 1 of them over the number, so R over 3. Okay, and what about the current? First of all, the power is given from VB squared over R equivalent. Okay, so P2 equals 3 VP squared over R. VB squared over R equivalent equals, yes, R over 3. So P2 equals 3 VP squared over R. So we managed to obtain the power in the second case in the parallel connection, and in the series connection now we can compare these two powers. So P1 over P2 equals, yes, VB squared over 3R, yes, over 3P squared over R, so it will be 1/9. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.